All right, guys, this is going to be the video for the rest of the 2.1 section. In the last video, we talked about polynomial functions and how to tell if something is a polynomial function. Here, we're going to start off by talking about a specific type of polynomial function and then kind of morph it into something else. So, a linear function is a type of polynomial function. It's got a degree of 1, and it's a function that you're probably fairly familiar with. You've studied it for a long time. It's the whole y equals mx plus b, or here you're seeing it as f of x equals ax plus b. So a and b are going to be constants. That leading coefficient is not going to be 0, right? And that means that we're not going to end up having horizontal lines or vertical lines. Everything's going to be slant or oblique. So what we're going to do with this is, you guys remember back in Algebra 1 and 2, and even in geometry, you guys dealt a lot with slope, and that came up just fairly regularly. And another word for slope was the rate of change, okay? We're doing that again. However, it's going to be more of it's not going to be the same way. It's going to be a little bit more involved, because we're no longer going to just do the rate of change of a linear function. We're going to use the same idea that we did with linear functions when we did the rate of change or the slope. We did the y2 minus y1 over x2 minus x1 formula. That's going to be pretty reminiscent of what you're seeing right here. Okay, it's kind of like the y2 minus y1 over x2 minus x1 situation. So with that being said, we're doing this. I know I said that this is so similar to what you did with slope, and it really is, but this is going to be the average rate of change rather than just the rate of change. Now, the difference there is that we are not going to be looking at just a line as my function. You may be looking at something entirely different, like potentially you could be looking at a function that's kind of curved like this, and they ask you about what is the rate of change over a certain interval. Well, this is not linear, so you don't look at this and think it has a slope. But if you look between a point and another point, right, there does exist something called a secant line. If y'all remember back to your geometry terms, there does exist a secant line that goes between those points, and I can find the slope of that. So if they ask you to find the rate of change or the average rate of change of a polynomial function, they'll give you an interval over what they want you to do that for, from this x to this x. And that is what you're able to use the slope formula for in order to solve for that average rate of change. So no, you're not finding the slope per se of the function. The function is not a line. However, we can look at the average rate of change between two intervals because we're able to make a little secant line out of it. Okay? Okay, so with that being said, let's go through some examples. Okay? We have example 2. It says find the average rate of change over the interval -1 to 3, okay, for this graph. And there's a graph kind of similar to what I was drawing just a second ago. All right, so I am going to redraw this just real quick so that we can get that on here. You don't always have to draw the pictures, but I think sometimes it can be helpful. I wouldn't worry about it being perfect, right? It's going through here. It's going back. Oops, I did that a little bit too wide. Let me use some white out. Sorry, I should have drawn this before I started making the video, y'all. It's my bad. Okay, so I'm going to just pretend like that didn't exist. That'll make it easier. And then have another point out here that the graph goes through. Okay, so again, that's not perfect, but it's kind of sort of close. They want us to look at the average rate of change over the interval, and they say -1 to 3, all right? Which means I'm looking at my x value of -1 to my x value of 3. 1, 2, 3. So I want my average rate of change over this interval, meaning I want the average rate of change from this point to this point. Something that's helpful is to know exactly what this point was. This is the point -1, 0, and this is the point 3, 4. So that's helpful to know because now you can do your slope. Again, it's basically the exact same thing as your slope formula when you do your y2 minus y1 over x2 minus x1. But the formula that we had looks a little bit different. Let me bring that back. Okay, because they're trying to put it in terms of your function. So this, remember your f of whatever, those are your y values. So this is saying f evaluated at b is the y value when your x is b. Okay, and then f of a, that is your y value when your x is a. So we have our points basically. We have y2 minus y1 over x2 minus x1. But the notation for this is maybe a little bit different. I'm going to look at this as being my point A, and that would make this y value f of A. I'm going to look at this as being B, and this guy is f of B. So that we can plug it in and use that same notation. So what I'm going to have here is I'm going to say 4 minus 0 over 3 minus a negative 1. Minus negative, remember to change that to be plus. And then we just clean this thing up. We've got 4 over 4, which is just 1. So my average rate of change is 1. Okay? Okay, let's look at another one because sometimes they don't give us graphs and we cannot be guaranteed to have a graphing calculator to help us. So how would we tackle this? Well, good question. We're going to look at, we've got certain intervals and we've got functions, okay? Now, you can end up using a graphing calculator to help you with some of the solving just to make things a little bit quicker. But you can also do this stuff by hand. So look at this. We're going to find, this is like my A and my B. That's what those 2 points are, or those 2 coordinates are giving you. That's my interval, A to B. Those are the X values that we're using for checking that interval. Well, I need to figure out what is my F of A, right? That means I'm looking at what's F of -2. And that just means that if you're going to solve that, you plug a -2 into the function. Wherever you see an X, I'm putting a -2 instead. So really, -2 cubed is a -8, but multiply that by a negative is a +8. 3 times -2 is -6. So really, I got 8 minus 6, which is 2 for this value right there. That is my f of A. My f of B would be plugging in my B value, which is a -1. If I plug that in, you're just replacing all of your x's with a -1. -1 cubed is a -1 times negative is a +1. 3 times a -1 is a -3, and this works out to be a -2. So what I have is I have my A and my B, my f of A, which was 2, my f of B, which is -2, and then we can plug it into that formula. So my slope is, okay, the slope of that tangent line, the rate of change, is going to be f of B minus f of A. So -2 minus 2 over my B minus A. -1 minus -2. And then we just work that out. Okay, we're going to say this is -4 over 1, which works out to be -4. That's my average rate of change. Cool? I'm going to go through the next one. I did give myself a lot of room, so I may have to kind of squish this one. Okay, so again, we have our A and B, okay, and we're going to plug those in. So I need to find what is H of A. That's talking about H of 1. If I plug in a 1, 1 plus 1 over 1 plus 6. This is 2 over 7. Kind of ugly, but it is what it is. If I plug in the next one, h of b, which is going to be h of 4, that becomes 4 plus 1 over 4 plus 6. That is 5 over 10, which reduces to 1/2. So those are ugly numbers, but it is what it is. We got to work with that. I'm going to say, here's my slope. We're going to have our 1/2 minus 2/7 over, we've got 4 minus 1. Now, the reason you're not going to like this is not because of the pre-calness of it, but it's because of the fractions, okay? So you're going back to 4th grade. How do you add and subtract fractions? Well, you got to get common denominators, okay? If this bottom number is a 2 and this one is a 7, the easiest thing to do is to change those both to be 14. I can multiply this one top and bottom by 7, and it becomes 7 over 14. And then this one over here, I can multiply top and bottom by 2, which would give me 4 over 14. And that's a whole lot easier to combine. This bottom number down here is just going to be a 3. Let's go ahead and combine those fractions up here. 7 minus 4 is 3. So that's 3 over 14 divided by 3. Okay, remember how you multiply or divide with fractions. You're going to multiply the top one by the reciprocal of the bottom. So this is 1 over 3. The 3's cancel out, and you are left with 1 over 14 as your average rate of change. Okay, I know that's kind of ugly, but it's just because of the fractions, not because of the average rate of change thing. All right, we're going to do another one. Here we have a table. Okay, we got life expectancy of U.S. females born in a given year. Find the average rate of change in the life expectancies between these 2 years. We're looking between 1850 and 2000. All right, so we have, honestly, this one's easier, I think, than the last one, because in this situation, 1850, that's the A that we're talking about, because that's the beginning of my interval. 1850, B would be the year 2000, which means that F of A is talking about 46.10. And F of B is talking about that 81.83. Yeah? What we do is we just take those values and plug them in. So my average rate of change, my slope here of this line, this little secant line, would be 81.83 minus 46.10 over 2000 minus 1850. All right, this works out to be 35.73 over 150. And if we divide that out, because we don't like a decimal inside of a fraction, that's ugly, we would end up getting 0.238. Okay. And if we put units with that, I know that's kind of weird, but we would say age years per year. All right. So just as a fun extra fact, these are talking about the slopes of those secant lines. But I don't know if you guys remember, we talked briefly about slopes of tangent lines, okay? And those slopes of tangent lines is talking about like an instantaneous rate of change. That's something that we've briefly discussed in another video. What I mean by tangent lines, if I just brought that up, what if I was looking at a graph like this and I wanted to know what is the rate of change at this one particular point? It wouldn't be going through any others. I'm only looking at the slope of that tangent line. Now, that's a calculus thing. This is something you're going to study in calculus, is how to get the slope of that tangent line, okay? Now, we can kind of estimate it by looking at teeny, teeny, tiny intervals, because what if I looked at an interval of like through here? That might be kind of close. It's not going to be exactly right, but it would be kind of close. And the smaller we can make that interval, the better we can get an estimation. So we have one more example that we're going to look at here, okay, on average rate of change. And it is a little bit messy, but we have this situation where we are going to be looking at throwing a ball, okay? And this equation models that situation, okay? We're looking at an interval of 0 to 5. And they want us to find the average rate of change over each interval, okay? So we can kind of get a really, really close estimation as to what these are. Now, I am going to run through it kind of quick because just either like the sake of time, and, this shouldn't take too long. But we're looking at these two values. Now, what I have done is I went ahead and I plugged these in to the equation so that I can find these values, okay? So I already have those numbers all ready to go to make this go a little bit quicker, but you can always do that on your own. You just replace t with that 1.1 and then work through what that is, okay? So I'm going to do my whole f of b. Remember, this is a and this is b, right? So f of b on this situation, let's see, I'll tell you what I got f of a to be when I worked this out. F of a was 25.1, and my f of b was 26.571. That was when I plugged the 1.1 into the formula. Okay, so I went ahead and did that math off camera. And now we're going to do that work. So we're going to plug this in. We're going to take our 26.571 minus 25.1. That's going to be over 1.1 minus 1. If we work through that, we end up getting about 14.71 for that value. Look at my next one. Okay, again, I did the math off camera for getting the f of a and f of b. So f of a is the same thing it was last time. We're starting with the value 1. So that was 25.1. F of b is going to be a little different because, look, this is a smaller number. So the interval is going to be smaller. Okay, when I worked through and put 1.01 into the calculator for that equation, I got 25.25151, which I know is a long decimal, but just deal with it, okay? Then we plug this in. We have 25.25151 minus 25.1, right? F of b minus f of a, and that is over 1.01 minus 1. Working through that, I got 15.151. Now, this is a closer estimation to what this instantaneous rate of change would be just at that one singular point, okay? Because we're looking at we want to know, we're just trying to see the smaller the interval, the more precise this number can get, okay? We're going to make the interval even smaller by looking at my b value of 1.001. So in this case, f of a, still the same thing, 25.1, but f of b ended up being 25.1151951. And then plugging that into your function, I would have done 25.1151951 minus 25.1 over 1.001 minus 1, which I know this looks ugly, y'all. But again, it's just plugging things into the slope formula, and you can use a calculator to get these decimal answers. 15.1, I'm going to rewrite that. 15.1951 is what I got for that one. Okay, I've kind of run out of room to work D on this side over here because of this little hole. So I'm going to work D a little bit lower down. I'm going to say, maybe I can get the F and everything here. So F of A still 25.1, but F of B this time, sorry. That's f of b actually, because they put the 1 second. F of a is actually going to be, when they do the 0.99999 or 999, that's going to be 25.0847951. Okay. So this time, my f of b, that is 25.1, and then we're going to subtract the other one. Again, I'm running out of space, so I'm so sorry. Okay, 0.847,951. We're going to divide that by 1 minus 0.999. And working through this, I got 15.2049. All right. So all of these numbers are super, super close. And what we're trying to get at is the smaller we can make these intervals, the more closer we will get to what the average rate of change would be, specifically at the point when t is 1. Okay, notice how close all these intervals were to 1. Okay. What we can look at is as the interval got smaller, this number got a teeny tiny little bit bigger, but it was not getting more than 15.2. Now, when I looked at it from the other side, okay, when 1 was my B instead of my A, and I looked at it from the other side, I got 15.2049. So it was a little bit high. So our question here for E, it says, what do you think the rate of change would be at t equals 0, or sorry, t equals 1? My estimation is that on this side, okay, when A was 1 for these three, it was getting closer to 15.2 from that side. And when I swapped and put A on the other, when I swapped and put A as my B, 1 as my B, then I had a little bit larger than 15.2. So that leads me to think that my rate of change would be about 15.2 at t equals 1. Okay. I know that's a little bit messy. This one is more of an AP type of question. So, if you're on level, I wouldn't stress about it too much. But it really is something that AP we need to make sure we get on. Okay, last thing, just some bit of notes. If your rate of change is positive, that means that my graph is increasing. Okay, so let's say that if my, when I'm looking at my graph like this, okay, wherever my rate of change is positive, if I was going to draw this in, that's increasing in that area, okay? If my rate of change is negative, that was decreasing at that point. Okay, another thing is they say if the rate of change of f is increasing, not if the graph is increasing, but if the rate of change is increasing. And that's a little bit different. If my rate of change is increasing, that's that situation we've talked about with concavity. When we've brought in the rate of change the one time before this lesson, we talked about concavity. Well, if I have something that's concave up, like a cup, right? This rate of change, my tangent lines start off with a negative slope. Okay, I can draw the next one in here, can go further along my graph. That is not quite as negative. I can go further along my graph. It becomes positive, and it becomes steeper positive. Okay, as I go along my graph, this guy was going from a negative slope to a positive slope. That is showing that my rate of change is increasing. That's concave up. Different than saying that the graph is increasing. The rate of change is increasing this entire time. The graph was only increasing from here to there. So there's a difference. We got to make sure that we're seeing that. If my rate of change is decreasing, look here, this is going to make concave down. So it may start with a positive rate of change, but as you look later on in the graph, that decreased. It went from being positive, less positive, to negative. And that gives me concave down. Okay. My rate of change was decreasing this entire time because as you draw more and more of them, that was becoming lower and lower. My rate of change was decreasing, right? That made this concave down. But that did not say that the graph was decreasing the whole time. The graph was only decreasing on this side. Okay. So those are two different things. Saying the graph is increasing and decreasing is different than saying that the rate of change is increasing or decreasing. So we got to try to wrap our brains around that change, okay, around that difference. If you're struggling with that, go back and rewatch and listen to me explain that one more time. See if you can get that to click, okay? All right, guys, that is it for 2.1. I will leave you to working on that assignment, and I will see you in the next one. Bye.